right, hello once again, Jeff Scott of Rankin Technical College. We're going over the online PDF book, AppInventor2, Create Your Own Android Apps by Wolber, Abelson, Spertus, and Looney. We're up to chapter 23 of 24, and this chapter, as you can see, is on reading and responding to sensors. In this chapter, as mentioned right here, we'll explore the AppInventor components location sensor, orientation sensor, and accelerometer sensor. Now, a couple things. The location is just that. Allows you to, specify a location. The orientation, I believe, is if you want to put something portrait or landscape. And the accelerometer oftentimes works if you want to shake the device. So along the way, we'll also talk a little bit about global positioning system, GPS, and a couple other math-related things. It's interesting. In my tenure as teaching, which has been several years, I get everything from people who tell me I want to be a programmer but I don't want to do math, to students who come in the first day and want to start programming games. The idea, if you're going to be doing anything that's going to involve any kind of arithmetic manipulation, you'll have to do at least probably some math. All right? Okay. Creating location-aware apps. Until the popularization of the smartphone, computing was on desktop lockdown. Laptops are mobile, but not in the same way. You don't carry them around and put them in your pocket like you can with your phone. Computing has left the lab and the office and is now taking its place out in the world. One significant effect of this is a new piece of data, your current location. Knowing where people are, as it says, as they move around the world has far-reaching implications and the potential to help us greatly in our lives. It also has the potential to invade privacy. The Android Where's My Car app from Chapter 7 is an example of a location-aware app. It lets you remember a previous location so you can get back to it at a later time. The app is private, meaning that your location is only stored in your database, so you'd use the TinyDB. Another good example here. You hear about people going out in the woods and going camping and maybe getting separated from one another or whatever. So as it says, a group of hikers might want to keep track of one another's whereabouts in the wilderness. This can eventually lead to other problems, such as, well, what happens if I run out of battery power or whatever? But that's a discussion for another day. So another type of location aware, as it says, uses augmented reality tools, which use your location and phone's orientation to provide something. So as it says, you might point it at a building to see its price on a real estate market. All right? You might want to walk near an exotic plant in a botanical garden to show you its species. We've also talked about that you might be in an unfamiliar place and you want to know the newest or the nearest, I should say, Mexican restaurant, let's say. Okay? So to create a location-aware app, as it says, you first need to understand how GPS works. GPS, Global Positioning System, as mentioned, it's generated via a series of geosynchronous satellites maintained by the U.S. government. As long as you have an unobstructed sight line to at least 3 satellites in the system, your phone can get a reading. The latitude, longitude, and altitude. Latitude is how far north or south you are relative to the equator. North being positive, south being negative. The range is -90 to 90, and they show you an example here. And in this example in Ecuador, it's just south of the equator. Longitude, whereas latitude was how far north and south, longitude is how far east or west you are of the prime meridian. East coordinates have positive values, west coordinates are negative. The prime meridian, as it says, which stretches north and south, is located in Greenwich, a town near London that is the home of the Royal Observatory, the organization that originally established the prime meridian as the basis for measurements for astronomers and navigators. And you probably have heard of GMT, which is Greenwich Mean Time. Longitude values range from -180 to +180, and they show an example of Russia, which is a positive value. AppInventor, as mentioned there, provides the location sensor component for accessing GPS information. Okay? It has latitude, longitude, and altitude properties. It can also communicate directly with Google Maps. Again, we've looked at these. We looked at this in our Where's My Car app back in Chapter 7. The event, as it says, is triggered the first time the sensor establishes a reading and each time subsequent that the phone is moved so that new data can be read. There can be a delay if you go indoors, if you're not connected to Wi-Fi, if you're around a building that's heavily concrete building, etc. Your phone also has settings in which you can turn the GPS off to save battery life. As it says, that's another reason that you might not be able to get a reading. So you shouldn't always assume that the location sensor properties have a valid setting until the location sensor .location changed event occurs. One way to deal with the unknowns, as it says, is to create a variable called last known location, initialize it to unknown, and then have the location sensor location event handler change that value as shown in this figure here, figure 23.6. By programming the location sensor .location changed event handler in this way, you can always at least attempt to display your current location. You can also explicitly ask whether the sensor has a reading by using the location sensor .has longitude block as shown right here. One common use, as mentioned here, of the location changed event is to check whether a device is within a boundary or within a set area, and that's the example they showed here. Such a boundary, as it says, has numerous applications. For example, warning parolees if they're near a legally specified distance from their home, alerting parents or teachers if a child leaves a playground area. All right? And there's all sorts of ramifications. I believe, I've said this before to my students, and sometimes they get either weirded out or we get into arguments about this, but I can see the day when a child is born that they have a chip embedded in them, be it in their arm or wherever, where you have all this information, which would make it darn near impossible for somebody to kidnap a child or do things they shouldn't be doing, and plus, you'd always be able to get a reading of where the child is. Now, some people would consider that maybe the ultimate invasion of privacy, and others would say, you know what, if it saves a life, it's worthwhile. An Android device can determine its own location in a number of ways. The most accurate way within a few meters is through GPS satellites. Again, you won't get a reading if you're inside, or if there are skyscrapers, or if there's other obstructions around. And remember, you need a clear path to at least 3 satellites so you can get the latitude, longitude, and altitude. If the GPS isn't available, or if it's been disabled by the user, the device can obtain its position through a wireless network. In this case, you must be near a Wi-Fi router, and the position you'll get is the latitude and longitude of the Wi-Fi station. Another way to get positioning is through Cell ID, which provides a location for the phone based on the strength of signals from nearby cell phone towers. As it says, it's generally not very accurate unless you've got a lot of towers, but it saves battery time, and if it's the only thing you have, it's better than nothing. The orientation sensor can be used for game apps or for a compass to see which way the phone is pointing. As it says, an orientation sensor has 5 properties, as shown right here, and the author says all of these are probably unfamiliar to most people other than possibly an aeronautical engineer. There's roll, and as mentioned here, roll is 0 degrees when the device is level, 90 when the device is tilted left, negative 90 when the device is tilted right. All right, so that's your left and right, kind of your horizontal. Pitch, which is mentioned right here, is up and back. Pitch is 0 degrees when the device is level, 90 when it's tilted down, 180 when it's turned over. When it's turned all the way over, pitch decreases to not minus 90 degrees and then down to negative 180 degrees. The compass, I don't know if that's azimuth or azimuth. 0 degrees pointing north, 90 degrees pointing east, 180 degrees pointing south, and 270 pointing west. That can be very important. Again, if I'm lost in the woods, I can at least, if I know that I've gone south, when I strolled off, let's say, I can at least point my phone so that I know I'm going north. So ideally, I'm going to be going back towards where I started. There's magnitude, the speed of a rolling ball. As it says, it returns a number between 0 and 1 that indicates how much the device is tilted. There's angle of a rolling ball, which returns the direction. So that's the number which shows how the device is tilted. This is the direction in which it's tilted. The orientation sensor provides an orientation changed event triggered each time the orientation changes. To explore these, let's write an app that illustrates how the properties change as the user tilts the device. So they create 5 headings, and then it looks like they put a sprite on here. All right, so you'd need the canvas, and then add an image sprite or a ball, but the idea is that you can move this thing around on the canvas and it'll show you exactly what is happening as you're moving it. Kind of a neat example, I guess. The previous example, the one we just looked at, moves the image left or right. If you want to allow it to move in any direction, you can use the angle and magnitude properties, so you'd add more to it. I'd already mentioned to you earlier as far as using the phone as a compass, and as the author says here, compass apps and apps such as Google Sky Map need to know the phone's orientation in the world, east-west and north-south. Sky Map uses this information to overlay information about the constellations at which the phone is pointing. These blocks show 4 possibilities: northwest, northeast, southwest, and southeast. The accelerometer, which is the last thing that's discussed in here, as it says, it's the rate of change of velocity over time. And you know this, they give a good example here. If you press your foot on a gas pedal or the accelerator, the car accelerates. Its velocity increases. An accelerometer, like the one in your Android device, measures acceleration, but its frame of reference is not the device at rest, but rather the device in free fall. If you drop the phone, it'll register an acceleration reading of 0. So the readings take gravity into account. If you want to know more about it, it says you'll have to look at other books. In this section, they just explore the accelerometer enough to get started. It says if you completed the Hello Per app in Chapter 1, we've already looked at the accelerometer sensor. In that app, you use the shaking event to make the kitty meow when the phone was shaken. All right, that might work fine for a phone or maybe even an Android device, but it does not work well if you are hooked up just to the emulator. Like the other sensors, as mentioned here, the accelerometer has an event when the readings changed, and that's the accelerometer sensor .acceleration changed event. And here are the different things that it can respond to. X-accel, positive when the device is tilted right, negative when it's tilted left. Y-accel, positive when the device's bottom is raised, negative when the device's top is raised. And Z-accel, positive when the device display is facing up and negative when it's displacing down or facing down. We know that if an acceleration's readings are near 0, the device is free falling to the ground. With this in mind, we can detect the free fall event by checking readings in the accelerometer sensor .acceleration changed event. It says you could use such blocks to detect when an elderly person has fallen and automatically send them an SMS message out in response. And they give an example here. In fact, it's probably something very similar to what happens in the old "help, I've fallen and I can't get up" type of an idea. So, in this chapter, we looked at sensors, and as mentioned, sensors are of great interest in mobile apps because they make it possible for users to truly interact with their environments. By taking computing mobile, you're opening up a whole new world of opportunities. However, you have to think carefully about how, where, and when you use sensors in your apps. Again, there are privacy concerns, as we talked about in the last chapter. Many people are worried about what you're going to be doing with their sensor data, the big brother type of an effect. But still, as it says, with all the options in games, social networking, traveling, etc., all right, the possibilities for positive implementations using sensors are nearly endless. All right, that's it for chapter 23. We're going to come back in a minute and go into our last chapter, so it'll be the last lecture, and that is communicating with the web. So I'll be back with that lecture shortly.